Okay, so we left off here yesterday, which is of course on Tuesday for our purposes. You will have an exam coming back to you, I think today in recitation. So your grades might be already posted, I don't know. But the TAs are working diligently on getting those back to you guys. I'll talk a little about the exam. The exam scores seem favorable, like almost too favorable. Maybe we need to reverse curve it. No. We'll let the grades stand as they are. But I was impressed, let's say. All right. So hopefully we'll talk more about that next week when everybody gets theirs back. Okay. So there's that rule. And yeah, we'll start right here. So a couple things with chapters 10 and 12. We have the so-called marginal distribution. Multiplied by that will be the conditional here. Okay, and you probably get a little bit of noise from me today as I got my new friend, I don't know, some kind of contraption to help keep it cool. So it's probably a good idea to get to class early and then catch some cold air. But up in the crow's nest, I don't know what's going to happen up there. So anyway, there's the probability calculation for two events. Take the marginal times the conditional. Excuse me. And it kind of works out that if you have two events, A and B, then B and A are independent if this occurs. What we're saying here is that A's behavior has had no impact on B. The chance for B is still the same. So that's pretty much just basically what we're saying here. So, given that it's raining in Dallas, the chance that you come to class is still the same. Okay? What happens in Dallas doesn't necessarily affect you as far as getting to class. So those will be independent events. Now, given that it's raining in Columbus, that might impact your decision or your speed with which you go to class. So those events will be dependent. All right, so here we go. O negative blood, which is ironically my blood type. You have here 39% of people are O negative, 2 unrelated people are selected at random. Find the chance that both have O negative blood. Well, all right, let's do this real quick. So the chance for both O negative and O negative, well, that's going to equal to the probability of getting an O negative person in the first place, multiplied by the probability of getting O negative given the first one was O negative. Now again, assume that this is a random sample of people, then theoretically what blood type I have has no impact on someone else's blood type. Okay? So if these events here, they must be independent. So what I'm saying here is that if the first person is O negative, what's the chance that the second person is O negative? Well, it's still just O negative in general because they're independent events. And yes, you'll need your calculator from time to time. 0.15 or so. Just 0.15, sorry. So that's all we're doing there. Two people being O negative will be 39% for the first person times 39% for the second person. You figure 40% times 40% is about 16%, so we're a little bit under 16%. So tree diagrams can help us organize our thinking as far as sets and events and so forth. So like a sequence, of course. So let's do an example. So construct a tree diagram for the previous example on blood types. Well, you have the first person, and then you have the second person. The first person can have O negative blood, which is 39%. But then the chance of not having O negative blood is 61%. And then we'll go on to the second stage. The same thing happens again. It kind of repeats itself. So the second person can have O negative blood as well. Do a different color. Or maybe the second person does not have O negative blood. O negative here is 0.39. O negative here is 0.61. Now this is for the sequence if the first person does not have O negative blood. Then what happens with the second person? Likewise, the other direction, if the first person had O negative blood, then you have 0.39 again, and 0.61 for not O negative. And so the tree diagram is a way to keep the probabilities organized. Because if you do it in your head, sometimes it doesn't always quite stay organized. So then you just follow out the branches. Remember, it's like, let's go to this example here. Probability of O negative. Probability of O negative given O negative for the first person. And then you keep on going. So you have these kind of marginal times conditional situations. Well, the first one is just our answer from before. Which is 0.1521. And then now we're saying here the first person has O negative blood, but the second one does not. So this will be like O negative, comma, not O negative, which is 0.39 multiplied by 0.61. .238. Then going down, we have the other way around, right? So you flip a coin twice, you can get heads and tails, or you can get tails and heads. So but it's the same kind of process, more or less. You have not O negative, comma O negative, which is 0.61 multiplied by 0.39, and I'm going to guess it's 238. And then lastly, you have the situation where what if both people do not have, or neither person has O negative blood? Well, that's going to be not O negative times not O negative. .372. And then that covers all four outcomes. You got two people, O negative or not O negative. We're not worried about necessarily their type A or type AB positive. Okay? And then hopefully, it's almost like a Punnett square if you think about it. O negative was 0.1521. Not O negative is 0.372. And then the green should be 0.238. And then that should cover all the outcomes. 0.238. Basically 1,000 or 1. So that covers everybody. So the tree diagram is one way to represent the probabilities. A Punnett square from your biology class is similar, or a two-way table is similar. But in this class for chapter 12, they're talking about tree diagrams, so just be familiar with that kind of representation. I guess it's time to go on to the next page. So let's see here. Our two-way tables are based upon probability rules, so that's good. And again, I'm not trying to bore you with the same old examples, global warming or what have you, or what's the other one? Whether two couples are married or separated, that sort of thing. It's a way to kind of show you how the knowledge that we're learning in class builds upon what we've seen before. All right? So here we go with this example. Here's an and question that we saw in chapter 6. Same kind of concept. What's the probability that a randomly selected respondent is a Midwesterner who agrees with the global warming issue? Well, let's see here. I'm looking at now the chance of being a Midwesterner and agreeing. That's going to be this guy here. And because I didn't condition on of the Midwesterners or of those who agree, it's going to be out of the total. And I think what we did back in chapter 6, we stopped right here, more or less. Maybe we converted to a decimal or a percentage, 16.65%. But we didn't have this kind of probability notation. So in chapter 12, we do all the chapter 6 items. But yet we throw in this probability notation. So that's the only difference there for the most part. We're just kind of formalizing our calculations. Aha. We're saying here a randomly selected respondent, so we haven't necessarily conditioned on those who agree yet. You're ahead of me. Now, if I say of those who agree, then you're in the right ballpark. Okay, so we're getting to that. Next, the or question. Go ahead and do this real quick. You should know this like the back of your hand. All right? The probability that it's Midwesterner or someone who agrees. And if you want to set it up as a fraction first and then later on go ahead and put it into your calculator, that's fine. But we'll need decimals at some point. Okay, anyone have an answer yet? Anyone brave enough? Yes, ma'am? Okay, 0.77, sure, 776, 777, take your pick. And again, now Dr. Beck always has like a follow-up question, so aren't you lucky? Explain to the class how you got that. Okay, so she said, let me go ahead and just take all these people who agreed and then add the 51. Yep, that works. Now, that's a nice, clever way. So gold star for you, right? So that's going to give you, I think, let's see here, what did I get? 732 plus 51 is 783. That's that. Who did the long way, the way with the formula? No one did the way the formula? Yes, ma'am?
I did like the probability of Midwesterners plus the probability of agree minus the probability of both dramatic.
Like that? And it should give you the same answer? All right, excellent. So again, both of you are right. So it's not like I got favorites here, right? So, but just kind of showing you how the chapter 12 does it, it will take all the percents who are Midwesterners, which is the 219 out of 1009, plus the 732. But because there's an overlap, I take that out once. 168, I think. And then either way, you get the same answer. So you might even see it like in decimal form, like 0.217 plus 0.7225 minus 0.1665 or whatever. Oh, the 1665, we saw that in the previous example, right? 168 out of 1009. So that pesky 168. There we go. Moving forward. Okay, this one here, I decided to kind of help us out a little bit. Oh, we're almost done with this chapter. Let's see. The probability that a Midwesterner agrees that global warming increased temperatures during 2011 and 12. Use the conditional probability rule. So, let's see here. Now, your name's here in the front? Kevin, right? Kevin said in the previous example, why couldn't you just take it out of like the 232 or whatever? But look at this one, Kevin. What's the probability that a Midwesterner, so we know the person's Midwest, right? If we know they're from the Midwest, then we don't care about these other folks. So it's out of 219. Out of those 219 right here, what's the chance that they agree? In chapter 6, we would just did this problem like that. 168, 219, you're done. Chapter 12 makes it a little more complex by using this formula. And I'm just going to talk it through with you guys a little bit here. So, A given M is, if I know someone from the Midwest, what's the chance that they agree? That's going to be, by definition, the intersection of the two out of the Midwesterners. Well, the Midwesterners' marginal total is 219 out of 1009. That's the Midwest. The agree and Midwest is 168 out of 1009. And you know this from way back when you were a youngster. When you divide by a fraction, you multiply by the reciprocal, right? So dividing by 219 over 1,009 becomes 1,009 over 219. Bye-bye 1,009. Hello, answer. So on a test, on the next midterm, on a final, you will not need to go through all these steps. Just kind of understand where we might get them from, if you will. I think we have maybe a couple more, maybe one more example. Okay, yeah, one more. So let's see here. Is belief in impact due to global warming independent of region? Well, the first thing we can do is say, okay, what's the chance for agree? The chance of agreeing is 732 out of 1,009. So if there was no relationship at all, it would be about 72% no matter where you lived. But let's see if, depending on where you live, that's going to impact that probability. So using our notation from before, let's use a different color. What's the chance of agreeing if you're from the Midwest? Likewise, let's look at one more. What's the chance of agreeing if you're from the South? If you're from the Midwest, that's 219, and we did that earlier. 168 out of 219. .767. If you're from the South, 374 people, 262. 70%. So going back to your notes, you have a rule. Show you real quick. Two events are independent if B given A equals B. In other words, A's occurrence has no impact on B. So we're just going to flip it around. So is it true that the chance of A given M equals the chance of A? So whether if you're from the Midwest, it doesn't matter. The agree percentage is the same. Not so fast. 0.767 and 0.725 are not equal. And then likewise from the South, so in the purest sense, these probabilities are not equal to the marginal probability of 0.725. So we cannot say that they're independent. So,
Isn't the 0.725 like an average?
Yeah, like 732 out of 1,009, right? So, well, hold up, I see where you're going. So, what we're saying here, in the purest sense for independence, this 70%, 72.5%, is proportionately allocated to each of the regions. Okay? But then, so this is, we'll say they're not independent. And so we'll say here that region does matter. Or now let's go back like 2 weeks, I guess it was. I think you asked the question. Well, in the purest sense, Dr. Baker, 72.5% and 70% aren't that far off. Right?
Yeah, so we need to add, look at all of them.
Right, right. And then 76.7 and 72.5 aren't that far off either. So they're not independent in the purest sense, but how dependent are they? We'll test it out later on in this course. Right? They're not purely independent, but is it a significant enough difference? That's later on in the course. We'll figure that out. All right, so that, my friends, is the end of Capítulo 12. Okay, we're back. So let's see here. Chapter 11. So we're almost caught up to where the syllabus says where we should be, in spite of all of our inclement weather and that sort of thing. And so then that'll be good because then it helps you with your homework and your quiz and keeping the ball rolling. So that's not so bad. So let's see here. The overview or the intro pretty much is 1 through 9 helped us look at data analysis, and you guys did a pretty good job overall with that one problem on the test about the brainwave activity and sleeping and alcohol, right? They were trying to make this claim that alcohol helps you sleep better, right? So they did a study. And it actually works out that alcohol kind of knocks you out. But then if you have too much alcohol, you have this restless sleep. So you guys did some analysis about the brainwave activity, and those who had the alcohol had more brainwave activity in the wee hours. But anyway, probability theory talks about the connection between samples and populations. And so we want to see if we have a representative sample or not. So here we go. You had this random rectangles activity, I think maybe like last week or week before. And so we have a couple options here. You take a random sample of 10 numbers from 0 to 10, and the average 6.7. And then the TA collects averages from 5 other students, and he finds the average of the averages. Which data set might have a larger range? Your sample of 10 or the TA's set of 6 averages? Move that over there. Now again, we can simulate that in this class, so I can have each of you guys generate the random data, and then I find the average and you find the average, and we kind of compare. Okay? So the way it should have worked like this, where you have your data set can span 0 to 10, and you got 6.7. But the TA is getting an average of the averages. So the TA might get yours 6.7. He might get someone else's 5.2. He might get someone else's 5.3, maybe 6.4 and 6.0. That's just one kind of quick example of what could have happened. Now let's give one more. It's will be 6. So we'll give a 4.9. So the range is considerably smaller. Okay? Whereas there, with one person, you can get between 0 and 10. Now the average of the averages has a smaller range to consider. So we're going to talk about that dynamic in chapter 11. Okay? So let's see here. Then which would you expect to have a greater likelihood of occurring? You obtaining an average greater than 8, or the TA having an average of the averages greater than 8. Okay, so let's talk about that for a second. So, which do you think has a greater chance of occurring? The probability that this guy is bigger than 8, we'll say U, or the TA having an average bigger than 8. What do you think? Right, exactly. So I'm going to go with this guy here. You have a better chance of having that number be bigger than 8 because the average of the average is getting closer and closer and closer to what it's supposed to be. So even look back here. Your range goes from 0 to 10. So yeah, you probably could get an 8, 9, 10. But look at the TA's average of the averages. He doesn't even hit 7. So how's he going to hit 8 or higher than 8? So I'm going to say this guy has a higher chance of occurrence, and now we're going to learn about the statistical reason why that works out, or at least the rules according to that. So we have some fill in the blank, not a whole lot fill in the blank, but some fill in the blank. Okay, so what we're going to do is use statistics to estimate parameters, and some of these you have in your notes. And we're going to scratch that little code. I'm not doing it this semester. So the statistics estimate the population parameter. That's good. And the parameter is a number that describes the population. And I tend to look at it like this. P for parameter goes with P for population. S for statistic goes with S for sample. So the P's line up, the S's line up, everybody's happy. And then I want to start doing that polling software, so hopefully we get that going pretty soon. And here's an example. All Ohio State students who support the president, the new president, I guess you could say, well, that could be a parameter. But if I ask 100 of you and ask you your opinion, then that could be a statistic. All right, let's keep on moving. A little more notation. So you have the population mean and the sample mean. So the population mean is this Greek letter mu, and you saw that before in chapter 3, like the normal distribution. And the population standard deviation is sigma. And the sample standard deviation. So you got this kind of sample population. And you have this X bar mu going on. And we're going to also learn later on about percentages or proportions. And there's this guy P hat and P. That's down the road. That's not critical for this chapter. Just spoiler alert, I guess you could say. All right, so there's this rule called the law of large numbers, and it says here that X bar is a random variable. So if X bar is a random variable, the sample means can take on a variety of numbers over a certain range. These are all little background facts, if you will. It's unbiased, and I gave you that word this time to save you from typing and writing things down. So you're never going to be off systematically. And here's an important part, I guess you could say. The more and more individuals from this population we sample, the sample mean should get close to the population mean. So that's the essence of the law of large numbers. You sample 2 people, not so much. 200 people, you should be getting closer and closer to what the true mean is. And so if you're getting closer and closer, that means the distribution is getting tighter and tighter. So you have a sample size, let's say X bar, with n equals, let's say 2. Well, it might have this kind of distribution. But then you have X bar, n equals 30. Well, everything's going to be a little bit tighter. So there'll be less spread in the data set because you're getting closer and closer and closer to your true estimate. Yep, that's what we talked about before. And then, of course, there's a picture in the book you can look at. Okay, so again, there's another comment that I kind of gave you. Let's see here. Yeah, so I gave you a couple of the words. So basically, X bar will get closer and closer and closer to the population mean mu. So your sample average height or sample average will get closer and closer to the population average. Okay, so who's looked through the notes from chapter 11 already? Anybody? Okay, that's okay. This character will play a role. Okay, more. All right. So you have the population distribution and the sampling distribution, the next bar. So let's see here. The population distribution is for all individuals, and the sampling distribution is just for the sample statistic. So let's see here. We will focus on sampling distributions. So X bar can assume a certain range of values with a certain frequency. Even our new friend P hat, we'll learn about this guy later on in the course, could assume a range of values as well. And because we're dealing with statistics here, these are sampling distributions. Okay, so here's the secret. Suppose that X bar is the mean of some random. This is a simple random sample. Simple random sample. That's what SRS stands for. Then the sampling distribution of the mean is standard deviation over radical n. So this guy should be sigma over radical n. Now, put on your Math 1150, Math 1149 hats, if you don't mind, or pre-calculus in high school. What is the limit as n goes to infinity of that function? Oh no, I thought I'd stop having to learn math. Who can recall? Yes, ma'am? What's that? Infinity. Now, not quite. N is going to infinity. Yes? 0. So why 0? Hoyas? What?
Anything over infinity goes to 0.
Okay, so you're right that it goes to infinity. Sigma over infinity. Infinity is some big number. Sigma is a constant. You divide by a big number, it gets smaller and smaller and smaller. It goes to 0, right? Now, you're like, well, that's not the prerequisite for this course. But the concept is still the same. The more people I sample, the smaller the standard deviation of x bar, right? That's what we're talking about. Suppose x bar has some distribution, it has some mean, some standard deviation. And again, that goes back to this slide here. You have n equals 2, now you have n equals 30. It gets tighter and tighter and tighter. Sorry about making you guys go back and forth. If I wrote on the board, I could just point to it on the board, but that's much. So a sample of 15 people versus 1,500. 1,500, a lot less room for error than the 15. We'll get through one major example, and then that should be good enough to help you guys get going with your tarea. Okay, so let's see what we got here. X bar is an unbiased estimator of mu. That's fine. Got some typesetting things to work on. There we go. X bar is an unbiased estimator of mu, so you're not going to be systematically off. Okay, and then here's the kicker from the very beginning of class. Because we have this dynamic going on here, the averages are less variable than individual observations. So that makes sense. And the more people you sample, the less variable the outcome should be. So larger samples are less variable than those with smaller samples. And this is all just kind of applying the theory into what makes sense for us. It's all set up. Set up. Yes. 1, 2? Okay. Is there a question, or is it more like a let me jot this down kind of thing? Okay, so how about what page is on your handout? I'm looking at page 3. Which box? All right. So is it the blank is about the blank in the population? Okay. All right. So the population distribution is about the individuals in the population, while the summary distribution is about the values of the statistic. So I guess I kind of paraphrase it in your notes, but paraphrase it too much. Don't be afraid to ask these questions, because then you're like, what the heck did he talk about? I don't know. I wasn't listening. Right? So go ahead and ask. But then I'm also getting to have it posting these, so you can always go ahead and reconcile later on, too. The worst question is the one that's not asked. All right, so let's see here. If the distribution is normal, everything's good. You've seen this before. Here's the key formula we're going to use in this chapter going forward, where you're going to look at your value minus its expected value over some standard deviation. And I call it the so-called appropriate standard deviation. And then there's our different z-score. And if you remember from your exam, negative 1.45 was probably a z-score, not a correlation, not a percentage or probability. Anyway, we just standardize the observations, the number minus the mean over standard deviation. That's no problemo. Okay. We have a new rule in town. There's this guy that the sample mean x bar has a normal distribution with a mean mu and sigma over radical n for the standard error. And so in the future, if you have your observation minus what you expect over the appropriate standard deviation, when you have one random variable, it's x minus the mean over sigma. But when you have a sample average, then it's going to be x bar minus its mean right there. And then you don't want to just divide by standard deviation, because we had this whole thing with the sample size. As the sample size gets bigger, we get more precise. So you want to divide by the standard deviation over the radical n whenever you deal with sample means. So I'm just taking this guy minus its mean, divide by its standard deviation, if you will. So that's where that formula comes from, equals z on the, I think it's going to be on the next slide up here, but it's probably in your notes already. So in chapter 3, we just did that. In chapter 12, we're doing this one here. Because sample means have potentially smaller standard errors or standard deviations. Here's the formula, kind of more explicit. And because you have your calculator, you're smarter than the calculator. So be sure, if you want to type it all in one step, you offset it with parentheses in the numerator and the denominator. Otherwise, bad things happen to good people. Yeah, we'll do this one example. Okay, so let's see here. You have women's heights for 64 and 3, I think. Yeah. And we'll say, I think 67. Okay. Which would be more likely? For one woman to be taller than 5'7", or for a sample of 100 women to have an average taller than 5'7"? Well, you're walking down High Street. Okay, that makes sense. You might see somebody taller than 5'7". You might see someone taller than 5'7" in this room. But if you took the average for 100 people, the averages for 100 people should be pretty darn close to 5'4", the average. So I'm going to go with this guy the same way we started off earlier in the class. Now, here we go. Very important, jot this down. This guy is very straightforward. What's the chance for one woman X being bigger than 5'7"? Well, it's just like a chapter 3 problem. So you say, okay, fine. (5'7" minus 5'4" is 3 over 3 is 1. Look in your chart. 0.8413 maybe. Let me double check. I don't know if I brought it. No, I didn't bring it. All right. So if you have your notes from chapter 8 or chapter 6, it should be in there. Chapter 3 rather. I think it's 0.8413. Yeah, that sounds right. Okay, so then you want the area taller than that. So that's going to be 1 minus 0.8413, which is 0.1587. Okay? How do you put this into your calculator for those of you with the TI-84 83? Raise your hand, let me know. Someone in the back who uses the TI-84 83? The normal CDF? What else? Okay, we got to get through this example one more before we go. Oh, yes, sir? Right, so I'm going to put 67 here. I don't know what the upper bound is. The mean is 64. Standard deviation of 3. Okay, 0.1587-ish. So that's the first one. Now, we got to get to this big money question. Now, suppose you have a sample of 4 women, okay? What's the chance that their mean height, not weight, is more than 67? Well, that's where we have to do the x bar minus the mean over the new guy. Because we're dealing with sample averages. So don't just stop with 3. It's 3 over radical 4. You have to include the sample size in some capacity. So far it starts out simple. 67 minus what? 64 divided by 3. But careful, we got the new guy in town. 3 over radical 4. If you feel more comfortable doing it piece by piece, that's fine. But you could do it all in one step. So that's 3 out of, what, 3 halves? Is that 2? Okay. And then this should be 0.9772. And so then you want the area bigger than that. So probability x bar is bigger than that. Is 1 minus. So you only have a 2%, 3% chance. Hold on 1 second. In the calculator, it's normal CDF, lower bound, upper bound, mean, and this time put in that new guy. Put the whole thing in. And it should still work. O228. Okay. We'll pick it up right here. And you can look ahead to the rest of the notes. And this guy comes in handy later on.
Where do you get the 0.9772 and the 0.8412?
Okay, if you have a Z chart, table A, there's a table A in our textbook that you have to, or you have type of 3 notes. I'll show you type of 3 notes.
I think I did